Hey, good morning. Continuing our discussion for p-n junction diodes, we look at a few more terms and quantities around the space charge region, and then we'll get into circuit analysis. So my goal is to finish up all the p-n junction electrostatics today, and well, maybe at least introduce circuit analysis for a few minutes. So let's go here. Okay. So we looked at the p-n junction diode in conditions of zero bias, reverse bias, and forward bias, right? And then we look at how the diode equation, that would describe these three biasing conditions. So in the reverse bias, when you're applying VD in the opposite direction to the anode, the cathode, meaning the cathode is at a higher potential than the anode, VD would be negative. Some negative value. And hence the term e raised to VD would reduce to zero, or at least be very, very close to zero. So the approximate diode current in reverse bias would simply reduce to the reverse saturation current, where the minus sign indicates it's flowing in the opposite direction, right? And this is due to the flow of the minority carriers across the junction. You're applying reverse bias, meaning the cathode is at a higher potential. Positive terminal is to the cathode, negative is to the anode. Electrons and holes are the minority carriers in the p and n type material respectively, and so they cross over the junction. And so diode current then is simply the reverse saturation current minus IS. So simply reverse saturation current. And of course, in zero bias, when it is at equilibrium, this is the state where no external voltage is applied. It is also the state when the diode is actually manufactured or fabricated. So, as you would expect, there will simply be zero. No voltage, no current. And in forward bias, we would have, we can break this down and we can simply have VT over VT, diode voltage over the thermal voltage VT. So E raised to VD over VT. The diode current would be an exponential function of the diode voltage. This also reduces to, and we are making approximations here, IS times E raised to VD over thermal voltage VT. So Q over KT, KT over Q. So Q over KT is 1 over VT, thermal voltage VT. N is typically 1, the non-ideality factor. And so we can reduce the expression simply to E raised to VD over VT. Yes. Charge. One thing. So you're asking about this Q, right? Yeah, it's just 1 unit charge. Standard charge. Particle, charge of the particle, charge of the electron. 1.6 10 raised to minus 18 coulombs. Yes. The reason I'm laughing is because in the next slide. So I wasn't laughing at, I was just laughing. Brought a chuckle. That's all. Yeah. No, it's good. I mean, I like when students are like, going ahead. And that's one of the reasons I have my previous slides and previous videos, on there. So if students want to jump ahead, then they can do so. So yeah, we would rearrange the terms. So the statement or the question being asked was, how would we find voltage given the current? And the answer would be rearrange the terms. So we would take IS on the other side. So it becomes ID over IS. Then this -1 becomes +1. And then you take the log of both sides, and we would obtain this expression. So ID over IS +1, and then log of that quantity, and of course, then multiply with VT. So we can find diode current given the voltage, and we can find the diode voltage given the current. If you think back to the first week, I stated, right? So the analysis of the circuits would use the same methods that we learned in 113, 211, and 212, except we have different models for different devices. And each model, the model that we decide to use, that you decide to use as an engineer, depends on your given application and the surrounding, surrounding environment. So in the previous slide, we said, okay, let's just take n is equal to 1. We ignore the -1 in there and make an approximation, right? And so there are several times that you will do that as an engineer. So in the next few slides, when we begin circuit analysis, we'll look at 4 different methods to analyze the same circuit, and we'll observe 4 of those results. All of those results are actually pretty similar. None of them is an exact solution, but depending on our application, we can pick and choose. Yes.
So like I was asking about the ditches, and I was like before you first like if I have like 2 diodes in parallel and I have 5 voltage that is higher than I get like saturation. Yeah.
Okay. Mm-hmm.
So those would still have to have the same. They would the voltage drop across.
Would be the same. So I think the question being asked is if you have multiple diodes in parallel, right? Actually, that's not how I should draw that. You have multiple diodes in parallel, then by basic circuit laws, they should all have the same voltage. The answer is yes, they would have the same voltage, but the current will change. For each diode, the current will be different. So the differing voltages are due to the differing saturation currents, IS. And the differing saturation currents are a result of the fabrication process. So again, IS is a result of minority carriers. Also, there is Zener effect and breakdown effect in the reverse bias. So that's a result of the manufacturing process. So the current can change if the voltage remains the same. And the same thing happens if you connect it all in series. If you connect it in series and the current remains the same, then the voltage across each diode would change. One of the 2 quantities must change. Otherwise, I mean, according to all known laws of physics and all known laws of circuit analysis. Yes.
Just like one more too, so KVL wouldn't like you couldn't apply KVL because it's like a voltage source and then a diode circuit, right? Because like if I want to apply 5 volts, I wouldn't drop all that.
No, we would be able to, because the voltage would remain the same. So the question being asked is, can we apply KVL in this parallel circuit? Actually, or series circuit, doesn't matter. But yes, we can. If they share the same 2 nodes, then the voltage is the same. Each diode also is modeled as an ideal diode with a series resistor RS. And this is something when we did lab 1 in the lab manual, we simulated, we ran a piece by simulation, and then we described, okay, we are using this diode. The diode has RS equal to 1 ohm. So there is a series resistance. That series resistance is the opposition to the flow of current. So it's modeled as resistance. And so this resistance Rs is different for different diodes. So it's a different current, but the voltage remains the same. If you separate out the diodes and you apply the same voltage to each of those diodes, I think I understand. If I think your question and your, I want to say confusion, but explanation that you require is, if I apply the same voltage to two diodes independently, the diode voltage drop in these two independent circuits would be different, right? But then if we connect them together, are they different or are they the same? But they would be the same. The current would change. The current through each of those diodes would be different. The current would not remain the same. Yes. It is inevitable, yes. It's Thanos. It is inevitable. IS is a result of the manufacturing process. So you get, because we have 10 raised to 17, 10 raised to 18, 10 raised to 20. That's a mind-bogglingly large number. We cannot design any device down to the single atom or down to the single charge carrier. That's the reason why. You could build two diodes right next to each other within a few microns of each, within a few nanometers of each other. There's no known method, no known human method where we can actually fabricate it down to the last single atom. And that's why it's different. Okay. All right. So the reason this is important is because we can see the diode voltage is directly proportional to the thermal voltage. Thermal voltage comes from the temperature, meaning this is directly proportional, meaning the diode voltage is directly proportional to temperature. Because Vt is K times T over charge Q. K is a constant, Q is a constant. The only variable in the equation is T, temperature. So as temperature increases, diode voltage increases. And so there is a, if we plot or take the change in diode voltage as a function of the temperature, it is very well defined. It comes out to be minus 1.82 millivolts per Kelvin. Okay. And so for those of you who were in my lab, we did a third procedure. The third procedure in the lab was the simulation of the diode voltage as a function of increasing temperature. So as the temperature increases, what happens to the covalent bonds? The electrons acquire more energy from the temperature, so they break free from their bonds, so more carriers are generated. Now, in the p-n junction, there are more carriers generated due to the breaking of covalent bonds, and so your current increases slightly. And so the voltage, if you recall from the data that you collected, what happened to that voltage? For those of you who are in my lab classes, decreases. And this is a very well-known effect. It's very well defined. It's very, actually, to use the term loosely, it is precise. And it has multiple applications. One of the most common ones is in digital thermometers. And that's why you have these digital thermometers that are so cheap, because you require just a few components mounted on a small piece of circuit board. And there's an excellent explanation example in the textbook. So please read the example and explanation in the text. One of the feedback comments, so I think this is a good time to bring it up. One of the actually there are several feedback comments. was, and it's unfortunate in hindsight, I should have expanded chapter 2 and broken it down into sections. So was that, chapter 2 and chapters 1 were given just as like one big reading assignment. And then chapters 3 and 4 and 5 and, so on and so forth, they are now broken down. But if you are reading chapters 1 and 2, and if you're reading chapter 3 right now, you would see the format that I'm following is exactly as it's laid out in the book, so that there's no confusion, right? So if I cover some material, the point I'm trying to make is if I cover some material in the class, it's going to follow the exact structure and path that's in the text. Okay, so I'm not deviating from that. So it makes it easier for students to follow along. So everything that I'm doing here, every slide that I have a title is a separate section in the textbook. So if I'm covering this in class, it's already there in the textbook and it follows the same structure. Okay, so students, if they're trying to jump ahead, just look at the slides and then look at the corresponding section in the text. Okay, let's see. 26. All right, so reverse bias. What happens in reverse bias? Right, reverse bias is right here. You have the space charge region. This is at equilibrium, so it's WD0. This is P. So plenty of holes with positive charges. This is N type. So plenty of electrons with table just shifted. Let's lock it down. Okay. Plenty of electrons in the N type. And then you have the depletion region. We have immobile ionized atoms. And I need to take out my notes. Okay, so what happens? When you apply reverse bias, P is connected, the negative end of the external potential, and positive here. What happens to the electrons in the N type? They're pulled away. Holes in the P type, they're also pulled away, right? Opposite charges attract. So the depletion region, the space charge region, is expanding. There are more ionized atoms created here. So this is the original. And these are the new ones. And so the depletion region expands because more ionized atoms are now being created. The space charge region expands, it becomes bigger. Okay, and that is shown right here in both directions. In the P-type material as well as the N-type material, more and more ionized atoms are now created. And so if more ionized atoms are created, the space charge region is expanding. That is where the electric field effect comes into the picture. So because the depletion region expanded, the space charge region expanded, there are more charges on both sides and they are immobile, they cannot move. So the electric field increases. And because the electric field increases, the voltage, the built-in junction potential also increases. And so this increase right here is basically in proportion to the reverse voltage that is applied. Okay, so phi j is the original junction potential. Silicon is like 0.6, 0.7 volts. Now you're applying a reverse bias to it. Let's say it's like 0.5 volts, 1 volt. Then your built-in potential now is increased by that amount. So VR is the reverse potential, the reverse bias voltage that is applied. Okay. The new depletion region, WD, is a function of the reverse bias voltage. So it's WD0 square root of 1 plus VR over phi j. WD0 is the original depletion region width. VR is the reverse bias voltage that is applied, and phi j is the original built-in junction potential. All right, questions? Yes, for reverse bias. Question being asked is whether this is for reverse bias. The answer is yes. And that would be evident by the reverse bias voltage or the reverse voltage. Yeah. There are a few other phenomena that take place in reverse bias and also in forward bias. So we're going to look at some of the most important ones. Yes. Mm-hmm.
Like some threshold, like
Reverse bias or forward bias? So we are applying, so your question is, or actually your statement is, we are applying a voltage in forward bias, and then so once it reaches a certain level, it stops dropping. No, in forward bias, we are basically applying positive charges to the p-type, negative to the n-type. So we are pushing the electrons and holes away from the external source, meaning you're pushing them towards the junction. So now they have energy to actually cross the junction in forward bias. I think we did an illustration here. Right here, forward bias. So electrons are pushed this way, holes are being pushed this way. And so now they have sufficient energy to cross over the junction. And when they cross over the junction, there's free flow of current. But that doesn't happen until the built-in potential, meaning the depletion region width, is overcome, unless they have sufficient energy to cross over the junction. And that for silicon, that results in a 0.6 volts level. Germanium is about 0.2 volts. And from that point on, there's free flow of current or high flow of charge carriers across the junction. But that voltage is required, meaning if you apply 1 volt, the diode is going to drop 0.6 volts across it. Yeah. In a sense, yes. So current is not technically flowing unless it crosses the junction. And that only happens once it crosses 0.6, 0.7 volts. I mean, if we have a setup that is devoid of all energy sources, meaning we just, dark shroud, and we apply a voltage, and you measure, let's say you try to measure the current, we might be able to measure some nanoamps or milliamps of current flowing through at slightly less than 0.6 volts. But yes, at that point, current increases rapidly, and there's a big jump up, like a straight line with a very steep slope. Yes. Direction of the thermal voltage. Oh, thermal voltage, not temperature. Sorry. It's the same. It's actually an Einstein's. It's known as the Einstein relationship, and it's basically the same direction as the same polarity as the diode voltage. But technically, it's used most as a constant. It's used as a constant in equations. Technically, yes, but again, thermal voltage is not something that is like a voltage that is measured, to the best of my knowledge. I've only ever seen it used as a constant. Like if you have an equation, it's known as the Einstein relationship. And to be honest, I have not read too much detail about, about the thermal voltage of its background. And most of the times, the applications that we use, it's used as a constant. Okay, so what happens when the reverse bias voltage increases to a very high level? Well, we achieve what is known as reverse breakdown. And reverse breakdown, what happens is, let's say this is the reverse bias characteristic. Then in the third quadrant, it's almost a flat vertical, not flat, sorry, straight vertical line. So reverse characteristics is a straight vertical line with a slope that is far steeper than the forward bias. The forward bias might be somewhere here. This reverse bias is far to the left. Typically, this would be around tens of volts. So the 1N4000 series, for example, is approximately equal to, and this is one of the questions in your lab. 1N4001 series is about 50 volts. You can safely apply up to 50 volts in reverse bias, and the diode would not be damaged. And diodes typically are not damaged even if you exceed this rating. Okay, even if you exceed this rating, they are not going to be damaged. Meaning when breakdown occurs, we typically say we do not want to go into breakdown, but even if breakdown does occur, there are a lot more other things going on. So it's dependent on the doping levels, depends on the actual physical design of the diode. But if it goes breakdown, the word itself has a negative connotation. It's breaking down, but it does not typically damage the diode. Yes. Sorry, that's 1N. 1N. The 1N indicates it's a one junction device. A transistor would be 2N. So 1N indicates a one junction device. 2N means it's a two junction device, like a BJT or an FET. Yes. And so where? Oh, reverse characteristics. All right. So there are two mechanisms that we look at in reverse bias. Breakdown occurs due to the Zener effect and avalanche. So there are two effects, Zener effect and avalanche effect. Okay. And both of those are distinct. So Zener effect occurs in heavily doped PN junctions, meaning there are a higher than normal amount of impurity charge carriers, impurity dopants, and as a result, there's a higher amount of free charge carriers. If there's a high amount of free charge carriers, the PN junction that is formed, the depletion region that is formed is narrow, is very narrow. Okay, so lots of charge carriers immediately start crossing over at equilibrium. Because of the number of charge carriers, the depletion region, the space charge region, is now very low. And because it is very narrow, when you apply a reverse bias current, it does not take a lot of energy for the charge carriers to cross over the junction. And so heavy current flows in the reverse bias. Okay, it does not take a lot of energy. So when you apply reverse bias, there are already existing charge carriers present, around the space charge region, around the depletion region. And what happens in the reverse bias is there are covalent bonds, the electrons in the covalent bonds acquire enough external energy from the external electric field that they are able to break free of their bonds and they start crossing the junction. And so that effect typically takes place in voltages less than 6 volts. The Zener effect is in heavily doped PN junctions. Heavily doped PN junctions. And the heavy doping results in very narrow, very thin depletion regions. Yes. But because it's heavily doped, it does not. It expands to a certain point. So the question being asked is, doesn't the PN junction, doesn't the depletion region expand? The answer is yes, it does expand. But it only expands up to a point, up to the point of breakdown, which is where designing of the Zener diodes come into the picture. So it's an excellent question. It expands to the point of breakdown. But because of the heavy doping, there are so many charge carriers present in there that now the minority charge carriers on both sides are able to cross over the junction. And the electric field that we apply is typically around few volts, but it's few volts per micron. So compared to like centimeters or meters, it's like 1,000,000 volts per centimeter. Okay. Few volts per micron would be about a few million volts for a centimeter. So that's a very high value for an electric field. And the electrons in the covalent bonds are able to break free. And because they're able to break free, they're able to cross over the junction in reverse bias. So it expands to the point of breakdown. But it is narrow to begin with. Okay, it's very narrow to begin with because of the heavy doping. And because it's very narrow to begin with, it expands only to a certain limit. And hence Zener effect is typically seen only in diodes 6 volts. Okay. And that's when another effect dominates. And that effect is known as avalanche. An avalanche effect is typically seen above 6 volts. So again, if it's a normal diode and we are applying a reverse bias voltage, it's not heavily doped. So the junction is not going to, you are not going to get breakdown for anything less than 6 volts, because there aren't enough carriers in there to observe that Zener effect. But let's say you keep increasing the reverse voltage. Depletion region keeps expanding. More and more ionized atoms are created on both sides of the PN junction. But when it's a very high level of electric field, electrons are now breaking free of their bonds. Okay. And more charge carriers are being created. So more electron hole pairs are created. Every electron that breaks free of its bond creates a electron as well as a hole, right? So more and more are created. Now, when they are free of their bonds, they are free to move. And because they are free to move, they are going to drift in the direction of the applied electric field, right? Holes are going to drift or move towards, in the direction of the field, and electrons move opposite. But the result is that they're moving through the lattice structure. And because of the high amount of the electric field that is being applied, they are now accelerated through the junction. And when they're accelerated, they're going to hit other atoms because they're moving around in a random path. And they hit other atoms. Yes. At this point, it doesn't really matter. So the question being asked is it minority carriers? The answer is yes. On both sides, in the p side as well as the n side, electrons are being ripped. So if electrons are being ripped, a hole is also being generated at the same time. So it's the n side you have electrons and holes being created. If it's a p side, you have electrons and holes both being created. And it's reverse bias. So yes, technically it would just be minority carriers because now they're attracted by the positive and negative voltages on either side. So it would technically be the minority carriers. But the result is that these electrons and these holes, they are moving through the lattice structure. These electrons are going to collide with the other atoms. One electron colliding with another one is going to dislodge one electron. Those two in turn are still being affected by the electric field. They are still moving to the structure. So one strikes one, creates two. Those two strike two more. Now there are four. Four creates eight. 8 into 16, 16 into 32, 64, so on and so forth. So it's a cascading effect. Hence, it is known as an avalanche. Hence, it's known as an avalanche effect. So at some point, all of those are going to cross over the junction in reverse bias. And because the effect is created due to the impact of these electrons, it's known as impact. Also, ions are being created. Atoms are being ionized, right? The atoms are fixed in place, but the charge carriers are being created. So once an electron leaves, it leaves behind a positively charged ionized atom, right? And so its ionized atoms are remaining. So it's also known as impact ionization process. So technically, it would be referred as avalanche breakdown due to impact ionization. Okay. Avalanche breakdown due to impact ionization. And in both cases, a large amount of current flows in reverse bias. A large amount of current flows in reverse bias. So Zener diodes, the purpose of Zener diodes is we use them in reverse bias primarily as voltage regulators because the voltage across it remains constant. The slope here, I would say, is exaggerated. Exaggerated. Okay. It's actually a very steep slope, even steeper than the forward bias current slope. So large amount of charge carriers cross the junction. You have a large amount of current flowing through for nearly constant voltage. And you will perform experiments in the lab with the Zener diode, and you will see how you can change the input voltage. The Zener voltage will remain near constant. It will barely change like a few millivolts. Okay, and this is the reason why. One more point about this is technically Zener effect takes place only in heavily doped PN junctions and at less than 6 volts. Our book says about 5.6, but I generally say 6 volts. And then avalanche breakdown takes over or has a larger effect at greater than 6 volts. But it is generally accepted that all reverse, not accepted, but generally referred to, all reverse bias breakdowns are generally referred to as Zener breakdowns, even though technically they are two separate mechanisms. So you have Zener diodes that are, that are rated like 2 volts, 3 volts, 5 volts, 6 volts. And there are Zener diodes that are rated for 9, 10, 11, 12, and higher voltages. Okay. But technically, the avalanche effect dominates at larger than 6 volts. Okay. Let's take a pause. Questions? Yes. If we increase the voltage, does it make the diode more conductive? if we increase the surrounding temperature, okay, temperature of the diode is increased, does it make the diode more conductive? What do you mean by more conductive? Yep. Yep. Yes. Yep. So if the temperature increases, then the diode voltage would drop because there are more charge carriers. So it's more charge carriers, then the depletion region shrinks just a little bit. So the space charge region is shrinking now. So the electric field drops a little bit. So the built-in junction potential drops a little bit. It's very small. It's minute. It's in millivolts, but it's very well defined. So for every increase in temperature, the diode voltage would drop. VD would drop. Yes. Yes. That's a good question. So I think if I summarize the question, it's like, can we use a regular diode in the forward bias as a voltage regulator? The answer would be no, because voltage regulation by its nature means we want to regulate the voltage that's going into our circuit, right? So no matter the fluctuations in the incoming voltage, we want the output to be regulated and be constant, right? We don't want it to change. But in the forward bias, there is change. There is appreciable change, right? You increase the voltage, the slope is, it's something like this. And I'm exaggerating the slope a little bit, but in the reverse bias, it's like almost, yeah, and I'm not drawing it correctly, but it's almost like a flat line. The slope is very steep. It's nearly a flat line. And we'll perform that experiment in the lab. When you plot the forward characteristics, you'll be able to see the slope, even visually without looking at just numbers. We can visually see there is a slope. And with the reverse bias, it's like almost a vertical line. Yes, but that's an excellent point. If it remains constant, we could potentially use it. But the forward bias voltage drop is a function of the material in the doping, so it's going to stay constant near 0.6, 0.7 volts. Yes.
And like on each side of the, so like
Decreasing? Yes.
and then so that's gonna lead to forward built-in junction.
In the forward bias?
Yeah.
Yes. Slightly lower.
And is that
The Zener effect is only observed in reverse bias, though, not in forward bias.
yeah, well, I'm just thinking like in general, just for like a forward bias.
I see. You see what you're saying. So it's heavily doped. The junction is narrow. Then in the forward bias, wouldn't it be less than 0.6 or 0.7 volts? Is that what you're asking?
I think that's why.
Okay. Yeah. And there's one more thing I need to cover. So, and that's diode capacitance. Okay. So in reverse bias, we are applying a voltage and the space charge region increases, meaning there's charge held on the P side and there's charge held on the N side. So if there are two separate charges being held, separated by some distance, then we can model it as a capacitor. And that capacitance is modeled and labeled as the junction capacitance. So before we talk about both, let's talk about how this is created and how it looks. So if you remember the silicon wafers I brought in a few classes ago, let's say this was the P-type material, sorry, N-type material. and we create a p-type material on top of it, or vice versa, it doesn't really matter. And so this is the top view, right? We have n-type silicon wafer, we create an opening in there, we implant perhaps boron, column 3 element. So now we created a p-type material in there. So if you're looking at it from the top, and you look at the junction between the two, now it's separated by charges, right? So if you apply reverse bias to this, charges are being pulled apart. I mean, depletion region is increasing, charges are being pulled apart that way. So the charges are increasing as a result of the applied voltage, right? Depletion region expands because of the reverse bias voltage. More charges are created, right? More ionized atoms are being left behind because the electrons and holes are being pulled away. That's why the depletion region expands. And so it creates a capacitance that can vary or increase as a result of the applied voltage. And so that is known as the junction capacitance. And that capacitance is a function of the voltage. So we can model a diode as a voltage controlled capacitor. And there are special purpose diodes known as varactor diodes, VARAC, varactor diodes, where we use the property of the diode capacitance. So the way it would work here is physical capacitance. C is epsilon A over D. Epsilon would be a constant. A and D are basically design parameters. A is the cross-sectional area. So in this case, if I was to create a 2D layout, not 2D, sorry, 3D layout of something like this, that's probably not really a good one. You have the N-type, and you have the P-type material right here. P-type material is a few microns. And then, of course, there is the distance between the two, right? There's some distance between the surface. So that distance between the two, and it's hard to make an illustration, be given by D. That's the width of the depletion region. Capacitance C is epsilon A over D. This D is the width of the depletion region, WD, which itself is a function of the applied reverse bias voltage, VR. The cross-sectional area doesn't change. That is a design parameter, right? You're designing the dimensions of your P-type material or your N-type material. So this would be fixed by design. But WD changes, depletion region width changes as a function of the voltage. Hence, the capacitance changes as a function of the reverse bias voltage. And that is given by this expression right here. Junction capacitance is Cj0 divided by root of 1 plus Vr over 5J, phi j. And Cj0 is the junction capacitance with no bias applied. Epsilon S A over WD0. Okay. Epsilon S A over WD0. Just a few seconds left. So I'm going to rush to this. In the forward bias too, we have a capacitance, and that capacitance is known as the diffusion capacitance. So the capacitance in the forward bias occurs due to, again, charges that are stored in the space charge region, right around the edges, right around the boundary. And it is a result, excuse me, it's a result of the stored charges at the boundary, but it is directly proportional to the current. So CD, diffusion capacitance, is proportional to the diode current ID. Okay. And we can insert a constant in there. That constant is known as tau t. Tau t is known as the transit time. Or the constant of proportionality for that equation. Okay, and so that is given by CD is equal to ID times tau t over thermal voltage VT. And these are both important parameters. So in PSpice, we can, if we have a specific model that we're trying to simulate, then we can specify transit time. We can specify our junction capacitance. We can specify our series resistance. And then there are a few other parameters that we can do, that we can specify. So PSpice is very powerful. Yes. Transit time is the constant of proportionality that relates junction capacitance and the diode current. It basically is a measure of how fast, well, not fast, but how the charges move or transit in the material. So charges are stored on either side. So when you apply forward bias, charges are moving. So when charges are moving, the transit time describes that movement. Okay. All right. So let's stop right here. I think I've gone over time. Apologize for that. And we didn't get to go into circuit analysis, but we'll do that on Monday. So Monday, there'll be a quiz. And based on the material we have covered this week, Monday, Wednesday, Friday, as usual. And then, of course, there's a Friday quiz today that is on material that's covered in the last 3 classes. Okay. So there is a homework that is due, and then there'll be a quiz on Monday based on the material. All right. Have a good weekend, and I will see you all on Monday. Yes.